live on YouTube. Thanks.
There's Ted.
Oh, great. Right on time.
All right. So let's get started. Welcome, everyone. Thank you all for joining us on this third edition of our Compassionate Math Seminar Series. I've already met a lot of you, but for those of you I haven't, I'm Namista, and I joined this group a couple of months ago. And as someone from a business background, I'm just honored to be here and learn that there's more to math than 1 + 1 = 2. Or maybe some of you will tell me that's not true, which we can discuss later. Before we begin, I'd like to thank Topos Institute for giving us this platform and their infrastructure. We couldn't have done this without you, so thank you so much. We also have some exciting announcements of what our group has been doing over the summer. So I'll hand it over to Priya first and then Ted to discuss. Priya?
Thanks, Namista. It's great to see everyone here. I just have a quick announcement regarding the seminar. So with Tim's help, we had created a seminar series in researchseminars.org. And all the upcoming seminars, including the current one, would be announced here. You don't have to have an account to view the seminars, or and if you go to the seminar page, you could see the live stream link, which is in YouTube, and also you can join the Zoom. So all the details will be available in this page. So that's my announcement, and all our talks would be available and live streamed in the Relatorium channel, YouTube channel, and you can find the recorded version of the talks, previous talks, as well as the current talk here, and all the talks will be live streamed. Thank you. Thanks, Namista.
Thanks, Priya. I'm just giving Ted, do you know how to give someone access to sharing their screen?
I think I have, actually. It seems like I do have. Let's see.
Okay.
It might be a default. Hi, everyone. Thank you for joining us. I just want to share my screen to show you a little slide I created for to announce and advertise the special session in the upcoming JMM in January 2025 that we've been given the opportunity to organize. So you can, this URL is a link to the slides themselves. So if you want to have access to the slides, they're linked to our emails in case you have more questions about it. It's a morning and afternoon session. So we have 9 hours of program at our disposal. 4 hours in the morning, 5 hours in the afternoon. Really exciting stuff on Friday, January the 10th. Sorry, there we go. This is the little abstract for it, which is a link that takes you to their program, or it should anyway. Yep, and if you search tools and methods, you find our session. This is it here, and our names. And also, move on to the next page. Preliminary, this could change, but preliminary plan is maybe to have half-hour talk and intersperse some discussion break. So we're looking to have at least about 14 talks, perhaps, yeah, well, plus or minus, I suppose. But this is rather preliminary. We didn't have to commit to that, but we do have room for several talks. Some idea of the types of topics we have in mind. This is just indicative, but again, you can have an idea. And here's the link to how to submit the abstract list. If I click it, it goes to the JMM website for how to submit an abstract. But again, if you're interested and you have any questions, please don't hesitate to reach out to us. Let me just stop sharing here, to any of us, and we'd be happy to help you with that. Thank you very much.
All right. Thanks so much, Ted. All right, so let's start with our topic today. So today's topic is super interesting, and I think also really a great example of some of the stuff that we want to do in our compassionate math research group, which is we aim to bring in current and diverse views in the world of mathematics. Today specifically, we're going to talk about the use of mathematical models to explore mappings between abstract and physical spaces. And we're joined by Professor Edmund Harriss from the Department of Mathematical Sciences and School of Art at the University of Arkansas. Edmund, thank you so much for joining us.
Hi.
Would you like to tell us a little bit about what inspired this topic today?
Yeah, so I at some point got very excited about different digital manufacturing machines, laser cutters, CNCs, and so on. And got frustrated with the software, and so started to use it to write my own. And I found this to be a very powerful way of thinking about mathematical ideas and creating ways to deal with mathematical ideas in physical spaces. And in parallel, a lot of my work has been around notions of illustrating mathematics and how to, again, bring mathematical objects into the physical space. And so this talk is sort of some naive ideas about that almost, and also a question of how to make things more formal and whether the language of category theory might work for the relationships that we can see, not between different mathematical objects, but between mathematical objects in physical spaces and experiential spaces versus in abstract spaces.
Amazing. And what do you think compassionate math means to you, and how does it connect to our topic today?
So to me, at least, doing mathematics has for a long time been something that's hard and is a struggle. And I think the notion of compassionate mathematics to me is partly recognizing that mathematics does sometimes tell you how stupid you are, and creating a space where you don't have the humans around you also doing the same thing. And so thinking about how do we remove the barriers for people challenging themselves and thinking about mathematics in that they haven't explored before, whether that's at the research level, at the school level, at university, but give people the space to explore and think about mathematics, and for it to be hard. And make sure that the barriers that we have are the real mathematical ones and not ones that we put in place by social or sort of political stances.
Awesome, powerful stuff. Before I hand it over to you, I just want to let everyone know that our seminars are meant to be great grounds for discussion. So please feel free to jump in at any time if you have a question or a comment. You can also use the raise your hand button over there, or type in the chat, and I'll be sure to bring it back up. We also have some dedicated time towards the end to have more focused discussions about this. All right, over to you, Edmund.
All right, thank you. Let me try and share the right screen. Yeah. Okay. So I'm going to go through 4 examples of sort of ways to think about relationships between abstract spaces and physical objects and imagery. And the first thing to say, during this, I'm going to talk somewhat about the specific mathematics involved in the examples. That is sort of relevant, but also not, if you don't understand particular terms or whatever, that is not a big problem. So we'll talk through some stuff fast for those people who know what's going on. So if you understand the terminology, great. If you don't, it's not actually the key point here, which is more to think about that relationship between abstract and physical. And I think the other thing that I would say is that one of the things that we find when pushing abstract ideas into physical spaces is that reality resists abstraction, and you have to be quite gentle in how you do it. And it's not about just sort of brute forcing. It's often about working out subtle and ways in which the abstraction can be realized. And the notion of illustrating mathematics is sort of very key in this. And I think it's a nice idea to start with, because it's essentially like a dual to mathematical modeling. In mathematical modeling, you think about a physical thing and you want to create a mathematical version of it that somehow reflects it. And if it's not working, that's because that you have to change the mathematical model. In doing illustration of mathematics, you have some abstract mathematical idea you're trying to create a physical version of. You're going the other way. You're going from the abstract to the physical. And when you do that, you're now, if something's going wrong, you want to change what's happening in the physical space rather than in the abstract space. So I think sort of setting things up in those sorts of terms, we think more generally about the role of mathematics in science and modeling, and thinking about illustration as well. We're not just going one way or the other. So I think that was that point. So now we come back to this image that you've been watching. And this is creating an example of the Mandelbrot set, and creating it as a stencil by using a laser to either fire or not fire at different points. And the laser is firing at 4,000 dots per inch. But the image that the laser is sort of being driven by is also 4,000 dots per inch. So you can think about in this image, this is the most precise Mandelbrot set that this laser is capable of creating. Every single pulse of that laser is driven independently by whether or not that point is in the Mandelbrot set or not. And so this is a sort of nice way that you're taking this sort of abstract image, this set of points as a subset of R2, and putting it directly into a physical object, a sheet of mylar in this case. And when you do that, you're using the way that you're going to create that object directly in the sort of process. So we know very clearly the relationship between the model we have here, this physical piece of mylar, and the mathematical object. Now, it's worth noting that this is all very clever. It's not actually a very good stencil. Luckily, this was part of the Mathamalchemy project, and you can see here, especially down to the bottom right, Tasha Pruitt luckily is a very good artist and was able to do a good job with getting this. But as I said, when you take abstract ideas, physical reality resists them and adds extra information. And in particular, in this case, the heat of the laser caused the mylar to bend slightly. And so you can see down in the bottom right, the stencil was not holding nice and rigidly. But you can see there's some nice sort of dots around the edge. If you know where to look in the Mandelbrot set, you might see, might not be sure whether they're dots or dust. There is sort of, there's some of the outlying sets are sort of very nicely represented as very small dots. So it actually does a good job on some of the outlying pieces. So this is a sort of simple example of what we might mean, but let's take this to a sort of a higher level and look at a 3-axis CNC like this machine here. And it has 3 linear bearings, and each linear bearing, you can think about that being controlled by a number. And those linear bearings are fixed in relationship to each other. And so you can think about those giving you a basis for an affine space. It's an affine space, not a vector space, because you can move it around and freely set where the origin is. And so now you have a mathematical model of three-dimensional space precisely modeled in a physical machine. And of course, you can move the machine to individual points, but then you can say, well, let's move that to a series of points. And you can see here, the machine is now cutting paths. You saw that the tool just went up and then down in deeper, and it's cutting the same path. This is another example of that, making sure that you're getting into reality cleanly. You don't want to just, once you put material in the way of this bit, you don't want to just run it freely. So you need to think about how the path you're doing will relate to the physical reality. But we've got the ability now to think about this machine in a mathematical space. And here you can see we've now stepped up to a more complicated machine. Again, now, in addition to the 3 linear axes, we have 2 rotary axes. So you can see here the object is spinning on a platform, and then that platform is also rotating. And so now as we carve into this, we can choose not just the position we're carving at, but also the direction that the tool is facing. And here, so what is the sort of mathematical model we might want to think about here? Well, one obvious one is to think about a point plus a direction. So you're thinking about sort of vectors in 3-dimensional space. And that would sort of give you R3 crossed with a sphere. But if you actually think about the machine itself, it's got 2 rotary axes. So it's actually a subset of a torus. It's only a subset because one of the rotary axes that changes the angle of the platform doesn't actually go all the way round, because then the tool would be in the wrong place. And actually, it turns out that thinking about this as a torus is sort of practically useful. It gives you better interpolation, for example, between points, because it's representing what the machine is actually doing. But here you sort of see realized, when we go back to that illustrating approach, the double cover of the sphere by a torus is sort of an important piece of mathematics happening in controlling this machine. And so this again gives us a space that we can do mathematics in. And so here we are now using that space to translate from an abstract world directly into the machine. And so here you can see it creating by surfacing, so that you have a flat end bit, and it's staying normal to this surface. And the surface it's carving is a piece of an algebraic surface. It's the Bath sextic. And the toolpath here was actually created on the algebraic surface itself. And so here is the finished piece. I will pause and show it. So this is that piece. So it's got several, you make 20 of these individual pieces, and then they're connected by brass rods. And so here we're wanting to think about this idea of starting with the algebraic surface and going to a physical model. Now you first want to think about a specific affine patch to put your algebraic surface in, and that affine patch then sort of gives you the information that you're going to use for the machine. Interestingly, the machine I just showed you has a vector space crossed with a torus, not an affine space, because the center of rotation gives you a well-defined origin. So a way you might want to do this is to go from an algebraic surface to a 3D mesh, and then you can 3D print that mesh. There's a variety of algorithms and systems that can do that. But those actually add their own processes. They take the mesh and they create a slice path, and then that slice path is going to be what drives the 3D printer. And so you'll sort of get it with each stage, you're getting further away from the object. In this case, we sort of put the algebraic surface into a space where we can think mathematically and then go from there to the cut surface.
David?
Yeah, I had a question. Is this mainly like a stream of numbers or vectors that you're sending to these machines, or is there any feedback from the surface itself? Or is there any input to the machine besides what the programmer started with?
It depends a bit on the machine you're using. The machines I'm using here, they have no understanding of what they're actually doing other than moving dumbly from one position to another. So there's no feedback back or follow.
And so they're receiving a stream of numbers basically that has been programmed in advance, and that's all they're doing, right? Okay, thanks.
Yeah, the code, it's in this language called G code, which is one of the oldest programming languages. It was created in the 60s, and it literally is a list of X, Y, Z, A, and C numbers for each point, where A and C are the two rotary axes.
And it knows that there's some distance, there's some speed that, like, this thing just repeats at a certain frame rate, receiving those numbers and moving to those coordinates.
So you tell it the speed you want it to move at.
No, but I mean, it's receiving these numbers at a certain rate, right?
So no, it's doing a little bit more, a bit smarter than that. So you give it the string of numbers, it plans a little bit ahead how it's going to move through the setup, acceleration, and so on.
Do you give it goals of where it's supposed to arrive by what time, or the time doesn't matter? You don't care how long it takes, just as long as it gets there.
So you set the speed you want it to be moving. And obviously with a rotary, that's a slightly tricky thing, because you might ask it to be going faster than it's capable of. So you could, if you wanted to cut a square, you just give 4 points and it would move around the 4 points. Or if you were doing a curve, you could give points every thousandths of an inch if you wished.
Right, you'll draw a line between every pair of points you'd give. Cool, yeah. Thank you.
So, and it's coming back to thinking about going from the algebraic surface to a space where we think about paths. In this case, paths with a normal to the cut surface. We could use something like that to go directly to 3D printing, sort of cutting out the 3D mesh and slice path. So it's not saying that this subtractive method is necessarily the only one, but we're thinking about how the machine works and using the working of the machine to get us closer to the mathematics. And so, yeah, that's the sort of second example. So this example, we're now using the mathematics and the relationship between the machine and the mathematics and the object in a sort of more complex way, but one where we can still follow the sort of process through to the actual machine. Conversation, for example, with David was thinking about how do we go from the abstract path we're given to what the machine actually does, how those motions go. So we've got a more complicated path, but one which we are following carefully in detail. Now, at some point, that becomes overkill. If you want to create a model of this surface, for example, 3D printing is going to give you something a lot quicker than the sort of process that I've just discussed, because it does allow you to sort of apply powerful generic black boxes. And so going on to my third example, here we have an image of a sort of geometric object. Here, the geometric object we're representing is a list of positions. Each position comes in addition with a radius for how big the dot is, and a color. So you can think about each of these points representing a sort of a point in 6-dimensional space, 3 dimensions of color, 1 dimension of position, and 1 dimension of radius. Also, the ordering here does affect things, and you can see that smaller dots come on top of larger ones generally. The ordering here is sort of, to a certain extent, what happened. I know that Kate's in the audience. I don't think we had, I can't remember whether we had anything more sophisticated, but so you can see here when it's being produced as an image on my screen now, there's a bunch of stuff happening around pixels and creating an approximation of this. If I could zoom into it, because it's, well, if it was a vector graphics version, the circles would stay circles as I created that image at different scales. And we're not and if I was to print this out, obviously that would be a very different way of realizing this image, but somehow the image that comes out of that process is close enough to the image on the screen. Now, if you start talking to people in print shops, especially in artistic print shops, where you're really trying to get a close relationship between the colors on the screen and the colors printed, there's a lot of work you actually have to do in addition to make sure that things really match up about inks and exact properties of the screen. So we're sort of saying now that's all stuff that could happen, but we're going to treat it as a black box. And so we're going to think now not about the whole process, but sort of trust certain things as we look at images. So what is this image? Well, here is a zoomed out version of this, and this is the complex plane, which you can also think as the upper half plane model of the hyperbolic plane. This, for example, is the square root of -1. Here you have cube root of -1 and sixth root of -1. So the real line comes along the bottom here. You can see that, and what are these? These are roots of cubic polynomials with a complex root. So it's the complex root of cubic polynomials. You can see, for example, there's lots of lines where they really don't want to live. There's sort of, you can see, this sort of unit circle and sort of other curves. And that's where thinking about this as the hyperbolic plane might be relevant, because these curves are all geodesics on that. And you can create various pictures. So here is one with sort of more structure. Yes, David.
Well, so the white is not a paint color. White is only where no paint color exists. Is that right?
And well, the points actually do fade to white, so you might have invisible points. But
oh, okay. So what you said, when they don't want to live somewhere, that will show up as white, though.
Yeah.
Okay.
Just realizing my battery is going down. Okay. So here we've actually chosen a slice rather than taking all cubics. And you can see that there's now some clear structure emerging. Yeah, Priya.
Edmund, so how do you know like which part of math is mapping to which part of the illustration? Like how do you, so you said like this is like square root of -1, like, so how do you know which part of abstract space is pointing to which part of physical space?
So we're choosing to create the roots and those are complex numbers, and then we're thinking about this being the complex plane, and we just happen to set the origin of the complex plane to be at the sort of center bottom of this image. This black circle is then the unit circle, and this is the square root of -1 because it's on the imaginary axis. So using the sort of Argand model of for complex numbers.
Thank you.
So we're seeing some, we're creating this thing where we're mapping the numbers individually, and they're scaled by 1 over the cube root of the discriminant. You can think about that as being a model of how complex the number is. So larger dots means you have simpler polynomials. Priya. Oh, sorry. This is an interesting one where we've added some additional information. And so each of these points is the root of a cubic polynomial. And so there's some additional information there. There's the notion of there's the real root that you also have. And in this case, the arrows are pointing along a geodesic from the point on the hyperbolic plane to the point on the boundary of the hyperbolic plane, which in this case is the x-axis, where the real root occurs. You can see all these points, all these ones pointing up. That's because those are pure quadratics, and so they're actually there is no real root there, and so they're pointing up to infinity. There's no sort of no suitable third root. So just to have a sense of what we might be seeing here, this is the same picture for the quadratics. And now you see those lines not in white, but in densely filled black. And this is the image that sort of started this investigation mathematically, because you sort of see some interesting structure here. You see geodesics on an upper half plane model, and you also see something that looks like a lattice in perspective. It's actually possible to sort of see where both of those things come from. So you can start off this grid here. You can think about that being the coefficient space for quadratics. So ax squared plus bx plus c is equal to 0. A, b, and c are each give us a dimension for this cube. We then look at this surface is where you have 2 repeated roots. And so on one side of that, you have a complex pair. So we separate those off. And then if you multiply all the roots by a constant, you don't, if you multiply all the coefficients by a constant, you don't change the roots. So that's where we get this perspective effect coming in. And so instead of thinking about this sort of grid of points, we only want to think about the points being lines through the origin. And that allows us to reduce to this disk of points with dots in it. So each of these corresponds to a polynomial, but now it's a sort of projective family of polynomials. You can multiply by a constant, you're not going to change the roots. Now comes the sort of fun part. How do we get from this image to the final one, which is the roots picture rather than the coefficients? Well, if we regard this as the Klein model of the hyperbolic plane, which is the model where straight lines are geodesics, we then and we transform from that to the upper half plane model of the hyperbolic plane, you have just solved your quadratic. And so solving quadratics corresponds to a translation between the Klein model and the upper half plane model of the hyperbolic plane. When we discovered this, we thought, well, that's really beautiful, but it must be really well known amongst people in the sort of communities who study these things. We would love to hear of anyone else who'd heard of this before. It's sort of a lovely coincidence between quadratic numbers, which are the simple example for algebraic numbers, and this sort of fundamental notion of hyperbolic geometry. And it was probably, maybe in the 19th century, it was well known when people were first studying these things, but it seems not to be that well known today. So, but the sort of to step out from this, the idea was that we started, going the wrong way, with this image. We were able to look at that and see some properties. And by looking at those properties and investigating, we were able to find interesting mathematics. And here, this is another example of that, where you have, so the blue dots are all quartics and the gray dots are quadratics. And you can see that the quartics might be on one of these densely filled curves, or they might be away from it. And it turns out that depending on whether they are or not is how well you can approximate a quartic by quadratic numbers. You can see that this dot here might be better approximated by the quadratics that are sort of densely filling than this one. And this was able to give a sort of nice, sort of clear idea as to why the quartic approximation splits in this way. This is another version, well, this is another way of visualizing the cubics that says, well, there's a really nice space that the quadratics seem to look at. The hyperbolic plane it works nicely. Can we find a similar space? And you can actually do that, the tangent bundle of the hyperbolic plane. So here represented as a torus. So each slice of the torus you can think about as a disk of hyperbolic plane. And then the tangent direction allows you to go round the torus. So this is the infinity direction. But this is where we need to start thinking about what we're actually representing, because we're wanting to look at something and understand it and then make mathematical conjectures on it. So we need to make sure that the thing we're looking at is really the abstract object. And so these two pictures on the left here, these are actually pictures of the same, trying to draw pictures of the same thing. And you can see if you sort of look around here, they look relatively similar. So that might, but if you look in the center, they're very different shapes. And the question, the difference is, how do we explore the limit of all these points? So here we build up as a cube, whereas here we build up as a ball. There are about the same number of points that we are projecting, or we are drawing. But in this case, you're sort of approximating on the diagonals faster. And in this case, you seem to be approximating slightly faster on the X and Y axes. But the sort of different behaviors come from how we're drawing it. So we couldn't, the sort of shape of these dots, other than saying they're harder points to approximate, we can't say what shape that's going to have, because it depends on the shape that we are dealing with. Whereas on the right, this is an image of large numbers of polynomials with just the coefficients plus or minus 1. And in this case, there really is a region around the square root of -1, which in fact you never completely get into. And so in this case, this shape is meaningful. So this sort of comes back to, we need to think about the whole process. We go from the abstract and the physical, then we study the physical, and then we need to bring back to the abstract, and we need to make sure that as we do that, there's something real going on. And to think about that loop, I want to finish with a fourth example, which is an artwork. And sort of having imposed geometry on a lot of wood, I love the way that the wood gives sort of form and soul to the geometry in many ways. And so I wanted to do something which was more of a conversation. And so this is a piece where the geometry of the wood is provided by the grain structure. So I put this slice of wood into my machine and took a photo of it, and then did some work to make sure that the geometry I was going to impose on this picture lined up with the actual position of the wood. So I actually, when I didn't take the picture dead completely vertical, but I was able to shear the image so it was squared up, which is why you see these different rulers in here. And so then I was able to take it into CAD software. This is Rhino, and draw in every fifth grain line. And then using those, I have an algorithm which starts at the center and draws lines out to the outside. And then when the lines get too far apart, adds in a new line. So you may be able to see two lines here, they're getting far apart. A new line starts, then these two lines, and a new line starts. Over here, you can see what happens. Sometimes the way the wood is behaving pulls lines together. And in that case, you get multiple lines. So you don't have the lines stopping if they get too close. You only allow them add in new lines. And so here is that sort of basic pattern now carved into the wood. So the wood is now always being carved at right angles to the grain. And here's the final piece. You can see, in addition to carving these lines, the further out they start, the deeper they start. And so they go to the edge. And so here, it's not really illustrating or modeling. We are taking something from the physical world, pulling it into an abstract space, adding some abstract structure to the geometry that was already inherent, and then pulling it back into the world. And so those are the four examples that I wanted to think about, but I now want to sort of open up the floor to discussion, and really to think about three questions around this. The first is sort of, what might it mean to put these sorts of ideas and maps into a robust category theory framework? What are the challenges around the sort of the notions of the physical world, which don't necessarily behave as nicely as category theory translating between mathematical, purely mathematical spaces? And then sort of secondly, like to ask the question, is that worthwhile? Given a way of thinking about this with category theory, what questions might ask, and how can we understand what's happening better? So are we creating an abstract model for the sake of having an abstract model, or are we creating an abstract model because that then allows us to do more powerful things back where we started? So is it useful to create a framework? And assuming the answer to those things is it's possible and it might be useful, is then, to sort of call for collaborators to think about this and work on how to actually do that. Yeah, David.
That's a really cool question. I like this a lot. And it seems like what you're doing is almost exactly right now the thing that you do with the wood, which is you look at it and then you write on it kind of, and then you work it and you see what it wants to do, because it doesn't maybe want to be cut with the grain or something. It doesn't work correctly. So then you do it for a while and then it comes back and it tells you something and you draw a picture. But now you're saying we're the wood in some sense, and we can, as modelers, we can put a structure on ourselves called category theory, which is an abstraction that may or may not fit the wood of the brain or the self or something like that. And we can work it and try it and see, does this help us make a beautiful picture when we kind of bounce back and forth between conceptualizing ourselves and actually being ourselves somehow. And it does seem somehow like you're asking a kind of a fractal question there.
Absolutely, yes. And I think, I mean, the delight of abstraction is you can always abstract on top of it. But also, and that's where the second question comes in. It's like, we can always build abstract models. There's lots of mathematical questions. What are the mathematical questions that are actually productive? So I also wanted to sort of give 3 ways in which I think this might be useful. And the first is sort of creating a more rigorous framework to think about mathematical illustration. And in particular, that notion of how we verify that the object we're seeing is really the mathematical object. So how do we create a check that we went from abstraction, in David's notion of thinking about our abstract selves and ourselves, as we go from the abstract self to the self, and then back to the abstraction, making sure that pair of maps really is giving us something meaningful. The second one is, I think this is a great way to make interesting mathematical art, and sort of explore things that can welcome people to mathematics, because you're thinking about the objects can exist and be interesting without the structure completely working. And the third is the sort of the sort of really practical one. I can do this stuff because I wrote my own code to run CNCs, and I am deeply frustrated by the lack of a theoretical understanding of machine control. And so whether we can use some of these ideas to create better software libraries for generic machine control and create a better sort of abstract space as sort of digital machining and manufacturing becomes more important, what is the right way to conceptualize that, which enables things to happen. And so I will now be quiet. And I also want to hear the discussion between people. So feel free to comment back. We have a couple of questions, so I'll hand it over.
Neil, maybe you can go first.
Sure. Thank you. Thank you, Edmund, for this talk. It was very inspiring, very nice works. I was curious whether you could perhaps reflect a little bit on your role and the role of your collaborators in creating these art works as you've described them, because I feel like as humans, we have certain biases, which I think thinking abstractly is a way we can avoid perhaps kind of falling into these biases. But once we put these things into physical forms, immediately we kind of ascribe to them, certain beauty or like aesthetic attributes. In particular, in the example that you gave with the polynomials, I was immediately thinking how do you pick the coefficients for the polynomial? Somehow you must have found a way to enumerate all the different polynomials, and that influences how the image looks that you're generating in the end. And then you had these three different images where you picked different coefficients, and they looked quite a bit differently. So how does that influence your work and how you look at these structures? And do you think sometimes perhaps it can also mislead you by focusing perhaps too much on the aesthetic aspects of the objects that you're producing?
So the first thing is that in the Starscapes paper, and we actually discuss it in the paper, we were shamelessly being led by aesthetic interest. We wanted to study pictures that look good, and if we could find a picture that looked good, we could then study it. But we were not. It's sort of, I think this is one of these places where the goal was not to the guide was whether we liked the image or not. The goal wasn't creating an image we liked. The goal was to say, if we create an image we like, well, what is it? Why do we like it? Why does this seem to have better structure? And then use that to go back and ask mathematical questions. So I think the first thing to do is to be guided by, oh, this is pretty to me. Firstly, it's motivating. If you find something attractive, working out why that is sort of something that you don't, it's fun. And secondly, but then you verify it by making sure, is there something that I'm seeing that I can really describe mathematically? I think the other aspect of it is that, working, as you said, with collaborators, if one person finds something interesting, then that sort of often, I often find that I rate my art based on how much effort when I put into it rather than the overall thing. So I have a version of things in my head. So having other people to look at it and say, well, I found this really interesting. And if other people go, oh, yes. So, for example, these algebraic starscape images were up in a gay bar in Reykjavik for several months. So people were dancing and looking at this mathematics. So the goal of making aesthetics part of it can also lead it to be in places you wouldn't normally expect mathematics to turn up. I think finding things that other people, the opinions of other people, it's not just your own opinion. And then also, with it being mathematics, looping it back through the mathematics and saying, what do I learn about the mathematics to say why is the discriminant better than the maximum coefficient, for example? Yeah.
But even in the mathematics, I think there is often a bias towards, formulas that are maybe more symmetric, that are more simple. They're considered to be more aesthetically pleasing to many mathematicians. And I wonder whether that is, in general, something in science where it was extremely successful, leading us to a lot of great discoveries. But perhaps there are areas where things are not as clean and not as aesthetically pleasing, but still worthwhile exploring. But that's just some thought.
I would definitely cite linear algebra as a great example of that. Gauss, for example, in the paper where he talks about the algorithm for Gaussian elimination, says this isn't mathematics. This is just some practical thing. And it's sort of, deeply powerful, useful mathematics that people didn't find attractive or interesting, and so it took longer to develop. And of course, those ideas actually go back as old, like where to the ancient Chinese mathematics had linear algebra already in it, different to the geometric approach. So.
Thank you.
In the interest of creating conversation, I'm sorry, I didn't mean to interrupt, but I think we're in the stage of talking with one another about this. I very much, I had it was in the tip of my tongue. I was going to talk about exactly what you just said, Edmund, in terms of the difference between being driven kind of by beauty as opposed to the goal being beauty. It's sort of a local as opposed to a global criterion almost. And then I love Daniel's. It really spoke to me, Daniel's point, because I've straddled in my years of practicing mathematics the pure and applied side, and people like to pigeonhole you usually. And one of the criterions I have found the most troubling is that you are doing more pure math when you're attracted towards the simpler, more abstract models, whereas you are sort of doing more applied math when you're, when you're embracing the complexity of the real world. And I think what you're showing us is that rather than being two extremes, they're almost like they come together in some way. They're sort of approaching. They're almost like flip sides of the same thing. What you trade off for seeming simplicity, you gain in abstraction, or vice versa. And to David's earlier point, I want to bring up this question. I wonder whether um, whether, for example, going back to one of your earlier, I think it was the first or second, maybe it was your second illustration, when you were demonstrating different ways, of cutting the surface. You were demonstrating a particular way, and then you said there are other ways, like, for example, following along, paths and so on. And I wonder if, considering the, for lack of, in air quotes, space of all possible ways to generate, to map into physical space and abstraction, might lead to deeper understanding. And whether you would consider that part of the utility of the exercise, so that if understanding entails, in fact, that multiplicity of approaches, rather than just seeing one end goal, but rather, it feels like you're understanding it deeper. If you can see past the specific instance of how you came to it, you understand the neighborhood structure of it in some sense. Does that make any sense to you guys?
Yeah, I think so. I don't know if anyone wants to jump in. Ted just asked a really good question about whether the pursuit of clarification and a more diverse way of looking at these mathematical models through these methods, I think, is what Ted has been asking, whether that's a worthwhile pursuit in itself. Any thoughts from anybody?
I have a related question to what Ted asked. So it's like, so when Edmund showed like the polynomials and the illustrations of the polynomials, how did that process happen? Like, did you start with the polynomials? How did you choose the physical medium to manifest that abstract idea? And how did you end where you ended up?
So we were at a semester program at ISOM. So we had both time and other people interested around. We and Kate Stang put up one of these images on the wall saying, what have you seen here? I then thought about, well, what happens if I try that with reduced cubics, and found, I get a similar but different image. What's happening here? And then just sort of exploring, starting to look at different families and plot them, we found lots of nice pictures coming up. So it was partly having that space where there were other people around, sort of to the point earlier, being able to find a picture. Oh, this is a nice picture, and then show it to someone else. And the sort of key point came when I created an image that was sort of, I'm now going to speak for Kate, who's just come on. I showed one and it was sort of interesting to her, not as a pretty image, but if she felt that there was mathematics in it. So maybe Kate, you can take up the story here.
I'll just interrupt a little bit where towards the end of the session, but we will be keeping this stream open. But I think we'll just stop the live stream now. But we can continue this discussion